Hi, I'm Eric Sublard, Vice President and Technical Director for Oracle Labs, and I'd like to give the Sigmod community an update on our work in integrating general purpose compilers with the Oracle database. 7 years ago, I gave a keynote at Sigmod on a vision for integrating databases and compilers, and I'd like to give a little bit of an update on what's happened since then. So last fall, we went production with GraalVM in the database, and the JavaScript engine supported by Graal can now run in pretty much the same way that PL SQL does. We call the database instantiation of GraalVM MLE for multilingual engine. In the bottom left-hand corner, you can see a snapshot of Apex, or Application Express, which is an in-database application builder, and where you could choose PL SQL as the way to build the business logic before. Now you have a choice of JavaScript as well. This is only really, though, scratched the surface of this opportunity, and we'll talk more about that. Now, adding a virtual machine in a commercial database turns out to be pretty hard, and that's why it's taken 7 years for us to get to this point. And let me give you an example of what conversations tend to go like when you want to concern yourself with manageability, supportability, or security of such a feature. Hey, we have this new feature we'd like to add into the Oracle database. Well, great. What does it do? It runs arbitrary program code in an arbitrary programming language inside the database engine. Okay. So tell me about its architecture. Is it built in the same way as the rest of the database? No, it's very unique. It's written in Java, but it compiles itself to native code rather than using JIT compilation like normal JVM. So it's not built in the same way that Java is, or in the same way that the rest of the database is as well. Well, this review may take a little while, and that's what happened. But we're here now. So I'll give you some background now on GraalVM and how we've integrated the database. So GraalVM is a multifaceted artifact. The core component is the compiler itself, which is fast, it's multilingual, it works ahead of time or just in time, and is written in Java. We have production backends for Intel x86 or for ARM in 64-bit mode. There's another tool called Native Image, which allows you to snapshot and build it or compile at build time rather than at runtime. And the small runtime library called Substrate VM is typically included in the output of that tool. There's an API called Truffle that allows you to write a dynamic language interpreter, or actually any language interpreter, and it automatically creates a compiler for you for the language when you write it to that API. There are polyglot APIs provided for exchanging objects between Truffle languages. We call that interop, and that's can be done with no overhead whatsoever. So a Java program can reference an object that was created from JavaScript natively with no copying and no proxy, or vice versa. And we provide common libraries for Truffle language implementers, such as dynamic objects that can add fields or add methods at runtime, and those components are shared across the different Truffle languages. GraalVM also provides implementations of a number of Truffle languages. For the most popular languages in the open source community, re-implemented on the Truffle APIs that allow for faster performance, as well as the multilingual interop for those languages. There are two classes of how we've done that with Graal. There are source languages like JavaScript, Ruby, Python, and R, where the Truffle interpreter interprets source code, and bytecode languages, where there's a pre-processing step that converts the language source into a optimized representation of bytecode or bitcode in the case of LLVM, or WebAssembly has its own bytecode format, and that itself is what's being interpreted by the Truffle API and not the source code itself. We also provide a set of tools for developing and debugging and optimizing Truffle-based applications and any Graal-based application. And we've also done integration primarily with Java frameworks such as Micronaut, Spring, Quarkus, and Helidon for higher level stacks that want more features beyond just the language runtimes themselves. So GraalVM can run code in 3 different ways, as I've alluded to. And all these methods can actually be combined in a single program. The first method for running programs is ahead of time with Native Image. The program's compiled typically at deployment time into machine code. provides fast startup, smaller memory footprint, and reduced CPU usage when the application is not running particularly long. This can be particularly advantageous for microservices or embedded use cases. There is a substrate VM runtime that provides features like the garbage collector in the binary. And the program's debug like other C++ or any other native language code with tools like GDB. So the usage model is you would first run the native image tool on your class file, and then you can run the executable produced by that native image compilation. The use case that's most interesting for native image is microservices in the cloud in Java, where you get a smaller footprint, especially for small microservice programs, and that can have a big impact on cloud costs that are often priced per megabyte as well as per CPU second. Now, Java wasn't initially designed for ahead-of-time mode, and so some JDK libraries needed some fixes, and there's some small spec changes to make AOT more mainstream that we're working on. And one key advantage of ahead-of-time mode is that you can initialize classes at build time. Now, Java normally uses objects on the heap rather than constants for concepts like enumerations, where those things require a class to be instantiated and put on the heap to capture enumeration for something like 1, 2, and 3. Those are 3 different objects with 3 boxes around them, and that has to get warmed up to create those things rather than being done at the compile time. The second mode that GraalVM supports is the conventional way you run Java programs, where it takes Java bytecode compiled with JavaC, and then you provide that bytecode to the Java executable, and it runs your program with JIT compilation. This is most suitable for larger, longer running server programs with larger heaps, and you can debug those programs with the standard Java tools. The classic use case for JIT compiled bytecode is something like WebLogic, and that's fully compatible with JIT mode. And then the Truffle API can run languages. And so, for example, Java, there's a Truffle implementation of Java. We can run Java in bytecode, or we can run it ahead of time compiled. Those are 3 different ways you can run Java. Now, this is the only way that we provide today, though, to run languages like JavaScript, Ruby, Python, and so forth. And Truffle provides for a higher level of optimizations, the things you do in SQL, where, for example, the shape of the data can change the compilation, or past usage can change the compilation. Truffle is also the base for our secure sandbox, where the Truffle language can be restricted in terms of memory, CPU usage, address space, and so forth. So if you don't trust the sandbox in terms of the code that was provided into the Truffle implementation, that code can be limited in terms of what it has access to, which is an important feature for any database. And for the Truffle languages, we also provide launchers that are interoperable with the standard ways that you run Truffle languages like JavaScript or Ruby or what have you. Now, I think one of the most important use cases that we've seen so far with GraalVM is Spring Native. So Spring Boot supports the GraalVM native image, and you can see that for Pet Clinic, which is their canonical sample app in Spring, they have a 4x reduction in memory usage from running in the Java mode, and 94% reduction in the startup time. And the cost, of course, that you pay, though, is longer to build the application. It takes a lot more analysis to initialize everything at build time. And so that's what makes it more suitable for a deployment time operation, as opposed to something that you do every time you make a change to your code. So to give you a little bit of context on the trade-offs between AOT mode and JIT compilation, we have this graph, and that's a little bit dated at this point, but this is still true today, that the JIT mode takes a while to warm up. So after 100,000 requests here, you can start to see a crossover point, and either the JIT modes eventually cross that and can exceed the native image, at least with the current generation of technology for native image. But if your application is not running for a particularly long period of time, then you have this big advantage in terms of throughput, because you don't have to pay for the warm up. And then you also have the reduced footprint benefit as well. A couple other use cases for GraalVM that I think are pretty interesting, particularly for the database. First of all, it's designed to be embedded. So because the program is already a Java program, you can create contexts to run instances of Truffle interpreters and any language that supports Truffle. And here we have a couple examples of 2 instances of the JavaScript engine calculating a simple program. And so you can build something like a spreadsheet with lots and lots of indications of some different cells that each could be in different languages potentially in GraalVM. Another really interesting use case that Graal supports is something that's near and dear to the hearts of most database people, which is separation of logical and physical data layout. And in the GraalVM context, that's done by virtualizing objects. So here I have some example code showing a computed array that's, rather than occupying physical storage, whenever you try to get the value in the array, it just returns the index times 2. We don't support modification to this array, and the potential size of the array can be the 2 to the 63rd minus 1. And here you can see that you can access any array member, and this is going to execute very quickly and not require any memory because it's a virtual object, doesn't require any storage in this particular case. But you could see where this could be useful in the database context as well. So for multilingual engine, in the database, we provide 2 modes of execution, and that parallels the way that PL/SQL works as well. There's dynamic MLE, where you provide an ad hoc snippet of language code in any MLE language, and that works like anonymous blocks do in PL/SQL. There's a package called dbmsSQL that does that for PL/SQL, and we have corresponding versions for MLE as well. And here's a few examples of what that might look like. You have here a context that you can create in PL/SQL and execute the context with a bit of source code that's going to call the console to output hello world from JavaScript and then free the context. And this also allows you to export values to and from PL/SQL and an MLE language using this kind of syntax here you see. And the context, as we showed earlier, encapsulates the entire program state for the instance of the program. It again allows in the database multiple contexts per session. And it also allows you to destroy context as well in interactive use cases like we see in Application Express. MLE also allows you to load code as modules deployed ahead of time in a persistent way. And you have to, in that case, provide a PL/SQL call specification to allow it to be invoked from, for example, a SQL query, a PL/SQL call statement, or from triggers. And that works in an analogous way to the way you create any other language you've seen in the database. Now we support JavaScript as an option, and any MLE language can appear here. And then you provide the body of the module, and then the PL/SQL call spec, and you get what you expect. So you can call this from a SQL query. MLE also allows you to import modules, JavaScript modules, into other modules in a way that's natural to JavaScript programmers, but allows you to create an environment to provide a set of modules accessible and use the database to manage that set of modules. And then there's a set of shared infrastructure that applies in both modes of operation, such as the SQL driver, SOTA, which is the document style API, MongoDB style ways to load data, particularly JSON documents, supports type conversion, shared environments, error handling, globalization, debugging, and features like that. So obviously the most important feature in any kind of code running in a database is the SQL driver. And that's the way it looks the same way you'd expect code to run outside the database, inside the database, with a few different changes. It's a synchronous API only. There's no promises. Everything's running in the database session itself, and so there's an implicit connection. It supports all the basic features from the driver, statement kinds, binds, batch execution, and so forth, and most of the data types. There's a few issues that have yet to be resolved there in terms of a few infrequently used data types. We support the JSON data type, as you'd expect. JSON is the most natural use case for using JavaScript. And here you can see access for from that from document-oriented data in the JSON database. Now, one issue that we've always had with integrating languages in database is the primitive types. So we support two modes in MLE. One is where the language itself provides defaults. So whenever you want to get a number in JavaScript, for example, the default representation for numbers is always a double, and that's always done for you. So the number formats in the database are implicitly converted to a double when you fetch them. Which can cause potential loss of precision and conversion overhead, but is compatible with all of the existing JavaScript libraries. Or we provide JavaScript objects with identical semantics to the PL SQL types that don't have any conversion overhead. But at least in situations where the language doesn't support operator overloading, that may give you different results than you expect when you try to call existing library functions. And so, so that may not be useful for as many different kinds of code. If the language supports operator overloading, then this can all work in the standard way with all the libraries. We provide an interaction mechanism to get errors out of JavaScript code into the SQL environment and vice versa. There's different error codes at the SQL level that can be caught. And then we provide a way to map language stack traces and back into the SQL and PL SQL context. Since those things aren't directly analogous, they are presented as a table to PL SQL or SQL programs. And you can catch errors bidirectionally. SQL errors can be caught from JavaScript side, or JavaScript errors can be caught from the SQL side. And we've also provided mappings in MLE for all the different database concepts to manage modules, manage code. All the DDLs have corresponding privileges, and we're using the same privileges that PL SQL uses. And we also support auditing of MLE statements, objects, and so forth in MLE. Okay, so that's what we've done to date. I think from the research point of view, what's interesting is where can we go from here? So what are the strengths and weaknesses of databases, and what are the opportunities? Now, I think one of the things that databases excel at relative to conventional languages is that they're more efficient for operations on large volumes of data. They provide features like implicit parallelism. SQL can scale out to hundreds of nodes. It's been proven that TPCH scales out very well, and analytics in particular. And it also provides for more efficient data structures with more optimized compression mechanisms under collections and so forth, relative to what you can get in a native Java, JavaScript, Python collection library. But databases, what they do is they simplify a certain class of engineering problem. They are picking algorithms and data structures for you based on the data, and they provide still what I consider the most usable concurrency model for dealing with parallelism, and which is a database transaction. And that's been something that's successfully implemented in millions of programmers, whereas locks and threads and the native language concepts are not as usable and hard to get correct. But the disadvantages in databases, like many other domain-specific languages, they limit usability, flexibility, and generality. The assumptions of the database runtime are more constrained, how parallelism works, how threading works, and these limitations and the types of code that can be expressed with SQL mean that people tend to pull data out of the database and other runtimes, even for operations that sound like the database would be good at them, like a join, often done in the mid-tier, because there's some little bit of extensibility that's not easily represented or executed in the database engine. So the research question I think that we still have is whether or not the general multilingual engine runtime can deliver on the benefits of databases while mitigating the lack of flexibility and generality when running in a database. If we can improve that while still keeping the advantages, then I think we'll really have something very useful. So what are the research directions we can take, what we've done so far into? The obvious place to go is to support more of the GraalVM languages that run outside the database: Python, Ruby, Java, and so forth inside MLE, and to support more of the cloud native frameworks and cloud infrastructure, Spring Cloud, New Quarkus, Micronaut, and so forth, making all that stuff work in the database, kind of obvious directions we could go into. Another way we could go is to provide deeper integration in the database. So PL/SQL and the existing Java engine in the database and our current iteration of MLE all require you to access database data via the SQL driver. And one thing we could do, though, is directly expose database data structures in the data layer, like the buffer cache and indexes and so forth, in native language idioms rather than requiring access via the SQL driver. So in other words, we could allow the VM to integrate the database in the SQL manner and not in the PL/SQL manner, leveraging the virtualization mechanisms in GraalVM. I think that could provide a number of advantages in certain use cases. Another direction we can go into is to increase the use of the query optimizer, or not just the relational optimizer, but the graph query optimizers and so forth, and in ways that can work with imperative languages. So bringing the things that the databases are better at into more native language contexts, like operating on Java or JavaScript collections or what have you. Now, this is done today in a limited form by a feature called Oracle Machine Learning for Python, where some kinds of Python programs can be rewritten into SQL, but the kinds of programs that can be rewritten are fairly limited. And so we could do a lot more in that direction. And then an additional direction that we think is also very interesting is to improve usability by avoiding the need for an engineer to decide at all when to even use the database. We can push down automatically collections of database or SQL executions into a collection that we reuse the same mid-tier code that may query the database, take the results of that query, feed it into the next query, and take that set of code and automatically move it to the database, which makes sense whenever local data dependencies can be hoisted either before or after the code to be pushed down. Obviously, if there's something like a big local shared concurrent hash table in the mid-tier, then that's referenced between the first and the second SQL execution. That kind of code wouldn't make so much sense to try to push down, because either you'd have to copy the hash table or you'd have a differing semantic. So that's another direction that we've been working on, and I think there are good opportunities to do things that way. So that's the summary of what we've done with Graal and the ways we're thinking about moving it in the database. And so we still believe that this is a great way to improve databases, is with deeper integration with compilers. And in the next 7 years, we hope to do a lot more. So thanks all of you for listening.